For those of you who don't know me, my name is Yisong. I'm a professor my day job, I'm a professor of computer science at Caltech. I also moonlight as an entrepreneur. Today, I don't know anything about longevity. I mostly work in AI. I collaborate with biologists. So I'm going to give you a more broader sense of where I think of the AI field. So to set the stage, because I know not everyone here is an expert in AI, I want to just talk about some of the paradigms that have been happening over the last 10 years. The first one is called supervised learning. What you do is you take a data set, it's hard to see, it's a image of a scene. I used to work in autonomous driving, where a human labeled every pixel in this image as car, street, pedestrian, etc. A typical self-driving car company collects millions of these images, possibly tens of millions, feeds into an AI model, and the AI model can decode predictions in the same semantic space as the labels. So this is how autonomous driving, got on its feet. Of course, collecting these labeled data is very expensive, so people want to avoid that. And so people take a large background data set that's unlabeled and use a method called self-supervised learning, where the AI model just learns properties or features of this unlabeled image data set, and you get what's called an embedding. And then you fine-tune this embedding using a few labeled data to get the same decoder. And what's interesting is that you can use maybe 1% or less than 1% of the labeled data and sometimes get the same accuracy. So this is a tremendous boon. And what happened since this time, which started around 2016, 17, is you get foundation models, which is essentially taking the same ideas from self-supervised learning and scaling it up to internet scale. So you take all of the internet, you take the pile, you apply these self-supervised learning approaches, maybe with some alignment. Self-supervised learning, by the way, is now called pre-training. These lingos change every 2 years in the AI world. And you get a foundation model, which is just basically these ideas scaled up to internet scale. And what's interesting is that if you pre-train your self-supervised learning model on text, such as large language models, you can train decoders by just giving instructions. So what you see is this trend of exponentially more efficient task-specific decoding if you want to deploy a decoder. And it is this trend that has caused so many people to be excited about AI. You can do it in autonomy, you could do it in knowledge work, you can do it in various scientific tasks. And big picture, of course, you can use these foundation models to revolutionize many aspects of science. Sam talked a lot about many of these. I want to take the time, because I'm an academic, to talk about some of the challenges that remain if you want to use foundation models for things. So if everyone thinks we can use foundation models for X, Y, Z, it'll be amazing. It can be amazing, but I want to tell you about some of the roadblocks. The first one is precision reasoning. So this is an example of just an astronomer taking some data and then realizing from this very, very partial, very, very incomplete data set that there's this concept called Kepler's third law. How can we get an AI to do something like this? And so one way to do this, which is not an original idea, many people are doing this, is thinking about self-improving agents using things like reinforcement learning. This is just one quick example that we've been doing in my group in collaboration with various medical researchers. We're taking real-world tools used by real-world biomedical researchers. This particular one is called CellPose. I'm sure many of you use it. We also work with others. And people spend months tuning these pipelines to make them work and deploy them in research hospitals and whatnot. And what you see here is the original image from, I forget which channels we're using here. But then the AI automatically discovered a way to pre-process this image before feeding it into the tool, which in this case is CellPose, that actually improves accuracy in a very realistic setting that can be deployed. So this is super optimization of workflows that can't be deployed in practice. And more generally, I'm very interested in this idea of using agents to design complicated workflows and complicated systems. And we've done this both in academic settings and also in entrepreneurial settings. I'm part of a new startup called Asari AI, where we're building AI agents for these types of engineering design. So if you're interested in that, I'm happy to chat offline. OK, the second challenge is multimodal reasoning. The majority of the training data for these foundation models is text. That was where the initial excitement started. And of course, nowadays, they can ingest a fair amount of images, but it's still quite poor in its ability to do precise reasoning in multimodal data. And multimodal data is extremely relevant in many areas of science, where this is just an example from astronomy, where this is the actual measurements from a telescope from a galaxy. And of course, you guys deal with crazy, blurry, noisy measurements all the time in your fields. And of course, this is also relevant in autonomy as well. I do a lot of work with NASA and JPL on things like autonomous driving of the Mars rover. OK, so what we need are new foundation models built from the ground up to much more intelligently extract the right amount of data from these super high-dimensional multimodal data sets. And so just to give you one quick example from a new project that we're just getting off the ground at Caltech, you can check it out. It's called Find3D. The demo is available on Hugging Face. What we do is we take any 3D asset. This is a 3D asset. Sorry, the video doesn't work. And what the model can do is do semantic segmentation in 3D. So you take an easel. It tells you where is the canvas versus the stand. You take a sneaker. It can tell you where is the sole versus the upper part. Of course, the model's a little bit noisy. It'll get better if you have more training data. And currently, there is no foundation model previous to ours that can actually do this in an open vocabulary way. This is just a few more examples. You can actually use an iPhone to take a photo of an object, do a 3D reconstruction, and then segment it. Okay, so this is an example. Of course, we want to do this for more than just 3D objects you find in a house. We want to do this for scientific data sets as well. So the third challenge is the data flywheel. So what we see right now is we get enough data. You could train a model. From the model, you can do reasoning. And what I think is really interesting is if you take this reasoning model, you apply it to generate more data, higher quality data, process data, refined data, clean data, that you can use to build a new model. And that new model can do even smarter reasoning. And this process continues. I think this is what we need to actually unlock the full power of AI across all of science and engineering. And so just to tell you how we actually trained Find3D, which is the model that I presented before, what we actually did was we took two existing 2D foundation models. One is called SAM, Segment Anything from Meta, AI. One is called Gemini, which is from Google. And we took a 3D asset, we rendered it in multiple viewpoints. We used SAM to segment body parts, and we color-coded as some special color, in this case purple. And then we used Gemini to tell us the body part of this. What is the name of the body part? And then you create a data set that looks like this. So you have a 3D object from a particular view. I know that these points from this view corresponds to the base of the snowman. And you generate millions of data. We generated millions of data points that look like this. And then we trained a brand new foundation model. So we use existing foundation models to train new foundation models. OK, so this will be my last thoughts. How can we build a data bank for biochemistry using foundation models? And one challenge is the screening challenge. So when I talk to my colleagues at Caltech, they tell me that the hardest part is after you run an experiment, or one of the hardest parts, you get something like this. This is, for those of you who know, this is nuclear magnetic resonance spectroscopy. And this is what you get. And from that measurement, you want to know, did my experiment succeed? Or what is it that I'm even measuring? And this is called an inverse problem, where you're trying to invert from the measurement the phenomenon that you're trying to discover. And this is something that I found very interesting, and we're building an entire benchmark across science, from climate modeling to seismology to astronomy to medical. It's called Inverse Bench. You can check it out if you're interested. And we're hoping to add more in the biochemistry domain as well. So that's it from me. This is the big picture. 3 points I want to emphasize: develop a data flywheel, use it to build better data sets, and self-improving AI. Thank you for your attention.
Thank you so much.
Yeah.
Are there any questions? Okay.
Thanks. Thanks for a great talk. Could you just elaborate before how did you use, again, the segment anything and Gemini? What did the final data set exactly look like?
OK. Is it possible to go back? Back one more. One more. One more. There we go. Stop. OK. So these are two 2D foundation models. 2D foundation models are more readily available. Are you familiar with SAM? Or?
Yes.
OK. So SAM takes a query point, right? Takes an image and a query point, and it gives you a segmentation mask, right? And so once it gives you a segmentation mask, you do a little bit of post-processing. You give it a special color, special ID. In this case, it's the color purple. And then you ask Gemini, OK, here's an object. What object? There's a sequence of prompts here, but like, what object is this? Oh, it's a snowman. What are the parts of a snowman? Oh, there's these parts. The part that's colored purple, what part is it? So there's a sequence of prompts you have to give it to get it to hallucinate less. And then it says, oh, this is the body of the snowman, right? And then that creates a paired data point, which is, then you back project this back onto the 3D asset using standard rendering geometric techniques. So this is the point cloud representation of the 3D snowman. These are the points that were rendered from this view. And these points, Gemini said, from the segmentation mask, is the base of a snowman. So then you get base. And then you train a foundation model that maps this thing, these points, to an embedding. And this embedding needs to decode base. I can explain offline more. Yeah.
Got it. Yeah,
Yeah.
thank you.
Thank you so much.
All right, thank you.